Okay, announcements. There's a lot happening in this class over the next couple of weeks. So it's worth just reminding people everything that's going on. It is very busy. So we have a lab that's been assigned. That lab is due on Tuesday. Tomorrow is going to be our study session, so please come to class prepared with questions for a study session. Friday is an exam. You have your project due a week from Friday, and then we have a final exam a week from Monday. That's a lot. So I will get a final exam study guide up for sure by Monday, so that you have access to being able to study for that as you finish off your last lab and your project. But yeah, there's a lot going on. We have a question in chat about the study guide, asking about whether we will be tested on abstract factory by itself, or just the difference between factory and abstract factory. And well, they go very hand in hand. So I would think that anything that I do with abstract factory, because this is how we presented it in class, would have to be based on some kind of existing factory implementation. So I reserve the right to ask about it kind of by itself, but it would be on top of an existing factory pattern. Of course, then I would also be open to testing, just asking you the differences between factory and abstract factory as well. But I'm not going to give you an abstract factory by itself with no underlying factory. Other questions about the study guide? Or about test preparation ahead of tomorrow's official study guide, or official study session? Okay, so last time we were in the middle of talking about the command pattern, and we talked about how to make commands, how to tie them to either physical or digital controllers. Either we used a remote as an example, but this can be any kind of controller. And then we talked about the final feature of the command pattern, which is the undo button. So we're going to store the last command that we did. And then we are going to make sure that we can figure out what is the last thing that was done, so that when we write a driver for it, here was the driver, that's the last thing we talked about. We zoom in on the actual results. We saw the difference between undoing when the light was off, when the light was on. Then we talked about more complicated objects. So we had a ceiling fan that had multiple different speeds, and we wanted to, with the undo button, not undo turning it on and off, but remembering the last speed it was at when it was on. So that's what the undo button did with the ceiling fan. So we had a high, medium, low, and off, and then undo just said we stored a field for the previous speed. On execute, whenever we changed the speeds, we would get the current speed, store it at the previous speed, and then update the ceiling fan to the speed that was executed. So the ceiling fan high command sets the ceiling fan to high. So we expect the ceiling fan.high to be what was done there. Were there any questions about this before we move on to the last very few slides of this, before we move on to the last design pattern pair that I'm going to go over in reasonable detail in the class? Hopefully this mostly makes sense. So we're going to test the entire thing. So here's the remote loader. We make a ceiling fan object. We make the associated commands. We're going to make a ceiling fan medium command, a ceiling fan high command, and a ceiling fan off command. We can set the commands on the controller, the remote for this example, So row 0 is going to be setting the ceiling fan speed to medium. Row 1 is going to be setting the ceiling fan speed to high. So we have a medium and off and a high and off buttons on the remote. Then we can call the on button was pushed. That is probably some listener for the actual remote pressing the on button at row 0. That should turn the ceiling fan to a medium speed. Then we push the off button, turns it off. If we press the undo at that point, then we should be returning to the last speed that it was at when it was on, which was medium. Then we push the on button for 1, which turns it from where it was medium to high. Then we can undo, and now instead of turning it off, it should go back to medium again. And sure enough, that's exactly what we see with our implementation of our code with the command pattern. We go medium, off, hit undo, go back to medium, switch it to high, hit undo, go back to medium. How are we doing with this? Does this make sense? Okay. It would be useful if we wanted to do a bunch of things at a time with a single button press. So for instance, we want to host a party and we want the party hosting button to be somewhere. And we want the party hosting to turn everything on and set them to the appropriate speeds. So you don't have to go down the remote and just on. You want a single button press to be able to do multiple things. So we want a single button to do a macro of things. So we're going to implement a macro command that allows us to do exactly that. So how do we do it? We make a new command called macro command that's going to take an array of commands. Since this is going to be some sequence of events that we're going to be specifying how we're going to do it, the constructor takes that sequence and sets the field to be the parameter sequence. When we execute now, instead of doing a single command, now we're going to loop through the list of commands and execute each one of them in sequence. Seems pretty straightforward. So that's everything that's inside of the macro command. If we look over here at what that looks like in a driver situation, we make a light, a TV, a stereo, and a hot tub. And we're going to make a light on command, stereo on command, TV on command, and hot tub on command. So 4 different commands. We're going to make a command array of party on that involves all of the ons and a party off that is all of the offs. And then we make a macro command for turning all of them on and a macro command for turning all of them off. We can then, on the remote or in the controller, dedicate some row to be kind of a party on and a party off that now does a list of commands rather than just a single command. Questions on the concept of putting these together? None. Party. All right, so how do we make sure that the party is working as we expect? We want to make sure we're going to look at the remote. We see that there is a macro command at slot 0 on the remote. We want to push the on button for the macro command. It's going to do all of the list of commands in the macro. And so as we push the macro on, we see that we turn the light on, we turn the stereo on, we turn the TV on. As part of turning the TV on, we set the TV channel to, I guess, the input to DVD, hot tub, heating, and bubbling. Great, so the party has started. So we can do confetti and bubbles. Party. All right. So command is useful in a bunch of different settings. So we end up being able to say something like we have an associated receiver and we have a set of actions. The receiver is like the remote, so we can pass around the requirements, we can pass around the concept of being able to execute those actions between different settings. So we can pass the remote and say, here's the remote with all of these commands on it. And you can pass just the remote onto some other scope. And then that scope has access to the remote. So suddenly they have access to all of the commands that are on the remote. So command is good for things like scheduling. Whenever you have some kind of scheduling of different processes, you can make those processes a command. And that way, when it's time for something to run on the schedule, you can then call the execute on that command that allows you to implement that. Multi-threaded applications is another really good use for this. So you have different threads doing different things, so you can call the execute on different threads and decide, okay, you are responsible for this command, this thread is responsible for this command. And now you have an easy way of divvying up the work between the different threads on your CPU. You can also use this to log requests. So if you receive a bunch of requests for things, you can use that to access those requests in a reasonable order. That's kind of like scheduling, but yeah, we basically just use a queue and the commands are in the queue. And once our technology has the bandwidth to be able to handle a new command, we pull the request from the queue and execute the command that's associated with that request. And you just continue to empty that from the queue. And that allows you to have a first in, first out way to execute those requests. What's nice is if a crash occurs as we're doing this, if we store an associated history of the commands that we ran, we can see the commands that caused the issue or a particular sequence of commands that caused the issue. So we see the order of execution that created the issue. Questions on how to use command for things that aren't just throwing parties? So this is another one of the fun design patterns that we have covered. This marks the end. We made it. Yay, throw another party. And what was it? I think it was this to peace out. Cool. So that's the command pattern. So what I would like people to do is I'm going to reveal a new survey to fill out on Canvas. I quickly go get that up. And I am interested in what you thought of this presentation type. So that is now live. You should see a lecture 13 post survey on Canvas. Please take just a few minutes to fill out your thoughts. As always, no right or wrong answers. I just want to know what the experience was like for you. If you're remote, I would appreciate if you would fill that out as well, since I think some of you were here for the first part of it. How are we doing? Anyone need more time? A little bit? Take a couple more minutes? Raise your hand or type still working if you're still working. Couple people, okay. No rush. Raise your hand if you're still working. All right, I think we're good to move on. Thanks everyone for the feedback. I do really appreciate it. My directed study student will also very much appreciate it. So this is the last couple we're going to be going over. These often pair together, so we're going to go over them in good detail. My plan for next week is to kind of do a very broad overview of the patterns that we have not talked about and just go into it. We'll kind of go over the refactoring guru pages and talk about how we can apply them, but at a shallower level than going deep into here's all of the code you should just in general have an idea of what these design patterns are and maybe a bit of when to apply them. So it's a bit shallower, but we'll just go through the remaining ones so you've at least seen them, you know what they are. And there will probably be a couple of work days next week as well, because I know I've thrown a lot at you and I'd like to give you some class time to work on that as well. So that's the plan for next week, after we get through adapter and facade. So let's first kind of compare or talk about how we handled something in the past. If we recall the decorator pattern, we had an object and we wanted to give that object some additional functionality. Instead of adding that functionality into the object, we decided we were going to make a separate interface and classes that extended from that interface, and then we could wrap a base object with these different classes to add that functionality to the base class. Let's have a what if here. We have a design that expects that it needs one particular interface. And what we give it is a class that implements another interface. So we want to be able to communicate about this object that inherits from one interface, but instead we have code that is written expecting another interface. So this is where the adapter comes in. We want to, kind of like a decorator, wrap an object in a class that instead of using the expected interface is going to use the implemented interface. And we basically are now adding the logic to convert one interface into the other interface. This is very much like an adapter on a plug. We have a 2-prong plug and we want to plug it into a 3-prong European outlet. So we can have an adapter that on one side takes as input the 2-prong plug and as output produces the ability to plug into a wall that has 3 prongs in European style. Right? We've now created the interface for converting one type of plug into another type of outlet where they're not initially compatible. If you use this adapter, it's compatible on one side for the input and compatible on the other side for the output. So you plug the plug into the adapter and the adapter into the wall, and now you have a plug to outlet communicator. But what's required is the conversion that is the adapter. So that's the idea, is we're going to convert one interface type to the interface, another interface type via a class that does that conversion. Does that make sense? Very much like a plug adapter. So where this would come in is we design a software system and we design it such that it works with our vendor's interface. But our boss, who is always looking to find ways to save money, finds a cheaper vendor and wants to now switch over such that our software is going to use and communicate to the other vendor instead of the vendor that we've been using for years. These vendors have different APIs and use a different interface for how they're going to be working together. Your options are basically to redo your entire system, go back through all of your code and change it such that it works with the new interface. Or you could instead write adapters that take the code that you already have and say, let's convert it now to say, if we already have code that works with this old interface, let's convert that output into the input that's being expected for the new interface. So all we have to do is write the converter. So shape-wise, basically we have the existing system that has a plug that kind of looks like a triangle and a vendor class that looks kind of like a circle. We can either try to reshape the triangle into a circle, or we could write a triangle to circle converter and then have the existing system communicate with the adapter and the adapter communicate with the vendor class. So think of it kind of like a puzzle. You can either force the piece to fit, but that's going to involve making changes to the puzzle piece. Or you can invent a new puzzle piece where you can easily put the two pieces on either side of that new puzzle piece as the converter. So eventually you get a system that looks like this. The adapter just fits in between the existing system and the vendor class, and now everything communicates flawlessly. But of course, the issue is in writing the adapter. You know what we haven't done in weeks? I'm sure you all miss this. No, it's not talk about pizza. It's talking about ducks. We haven't talked about ducks in weeks, and it's time for us to talk about ducks again, because this works way better and is way funnier with ducks. So the problem is, if it walks like a duck and quacks like a duck, then it must be a duck. Except now, if we use an adapter, if it walks like a duck and quacks like a duck, then it might be a turkey wrapped with a duck adapter. So the idea is we now want to add a turkey class to our existing duck hierarchy. We're gonna go back to our strategy pattern code when we talked about different types of ducks. And now we want to force a turkey into our duck system. And turkeys don't do what ducks do. So we need to write an adapter such that we can dress up our turkey like a duck so that it confuses other ducks. And they think that this turkey is actually a duck. So as before, we're going to start with a very simplified duck implementation. All a duck does is quack and fly. So this is our interface for a duck. Two methods, quack and fly. All ducks must do these things. So here is an example of a mallard duck. Note that we're not applying the strategy pattern. This was from before the strategy pattern. We're not going to consider the strategy pattern. That would be a separate thing to consider at this stage. A mallard duck quacks by printing out quack, because a mallard duck is a duck and quacks. The flying, of course, a mallard duck can fly, so it prints out I'm flying. The turkey interface can fly, but gobbles instead of quacks. Turkeys don't quack, they gobble. And turkeys can fly, but they can only fly short distances. They can't fly quite like a duck can fly. So we need some way to adapt this turkey into a duck in some way, shape, or form. Here's the actual wild turkey class. It implements gobble, which prints gobble gobble, and fly, which prints I'm flying a short distance, because that's all they can fly. They can't fly the same way that ducks can fly. So we're going to write a turkey adapter that is going to plug and play. It'll use what a turkey already does, but it needs to convert what a turkey does into what a duck does, so that the turkey can play with ducks and confuse them into thinking that it's a duck. So thinking about this, which interface should we implement? The turkey adapter is going to implement what interface? You kind of have two options. It either needs to implement the duck interface, or it needs to implement the turkey interface. Then think about what fields and methods do we need to be able to do this. So take a best stab at this, figure out what interface we're implementing, what fields do we need, what methods do we need.
In
Yeah.
the turkey interface, did we have a fly method also?
Yeah, we had a fly that did a short fly rather than a long fly. What do we think? What's the interface we're gonna implement? Duck. Who thinks duck? Who thinks turkey? Who has no idea?
Can we just use, doesn't duck have a bunch of physical radios, like quack, fly, whatever most of it is?
So,
Because
yeah,
like the basic born rate, except with quack, it's callable, turkeys can't really fly, except.
yeah. So to make the adapter, we want a turkey to be able to do everything that a duck can do, and then we just need to specify how that's actually going to happen. So we want to implement the duck interface because we want to implement and convert what a turkey already does. The adapter wants to give you the output of what a duck does. So we're going to implement the duck interface. What fields are there? What does a turkey adapter need to function?
Turkey.
A turkey. That's it. All we need is a turkey. What methods do we need? Quack and fly. Since we're implementing the duck interface, we want a turkey. Basically, what we're going to do is we're only going to call the turkey's methods, but we need output that's going to give us what a duck does. So we get something that looks like this. So turkey adapter implements duck, we have a field that's a turkey, and we make sure that we implement quack and fly. Since we know that a turkey can only fly short distances, we need to do lots of flies to emulate what a duck does with a fly. Unfortunately, we can call a turkey's gobble a quack, which is kind of all we've done here. We call the turkey's gobble, but when we say, hey turkey, quack, it's gonna go, and it's not quite what you would expect. So it's not going to fit in with a duck yet, but hey, at least now it responds to the quack. Whereas before, it was kind of the Simon Says, where now it's like quack, and it wouldn't. Because it doesn't know how to do that. Now it knows how to quack. It's just that the quack is a gobble. Does that make sense? So a driver to test this out, we're going to make a duck. We're going to make a turkey. And we are going to make a turkey adapter, but note it's a type duck. That looks a little bit weird. Duck, turkey adapter equals new turkey adapter. So we're storing it of type duck, and since it implements the duck interface, we can use polymorphism to do that. A turkey adapter is a type of duck. It takes in the turkey, and now we have a turkey that is inheriting, is implementing the duck interface. That's the first step to dressing a turkey like a duck. So now we can print the turkey says, and the turkey can call its own gobble and fly. We can say the duck says, and now we can print out what the duck does. We can print out the turkey adapter says, and now we can test the duck, duck.quack and duck.fly by passing in the turkey adapter, which then basically is converting what the turkey can do by calling the method names of a duck. So this is a basic adapter. If we wanted to see what this looks like in output, the turkey says, gobble, gobble, I'm flying a short distance. The duck says, quack, I'm flying. The turkey adapter says, now when we call the quack, it gobbles. And when it flies a short distance multiple times. And that is how the turkey does its best at emulating a duck. So it still can't make the quack sound. It at least can respond to a quack command. Questions on what we've done so far? This is a great idea for what to do for Halloween, by the way. So here's the pattern in its very simplistic glory. We have the client needs to send a request to the adapter. The adapter is going to translate that request to something that interfaces with the adaptee. And then we send the translated request onto the adaptee, which is then going to do what the client wanted. So we're just converting the request into a translated request. Another way to think of this is it's like Google Translate. If you're in some country that has a language that you do not naturally speak, you can ask the request in a language that you do speak. Google Translate will translate that for you and then play the translated request. And now you have a way of communicating with someone who does not speak your language or a language that you know. So the client makes a request, the adapter translates the request, and then the client receives the results of the call and doesn't need to know that the adapter did anything. Think of this like it's not a back and forth communication. If you have Google Translate sitting on the table and you're at a restaurant in France, I don't know, I don't speak French, and you ask, I would like number 18 large. And then you put a wall there. Let's say there's a wall. It translates it for you. The waiter receives the order in French, knows exactly what you said, and when the dish is brought to you, it's a number 18 large. Great, you got what you asked for. You don't need to know that the adapter was there, that a translation took place. You just know that you asked for it in a way that you know how to ask for it, and you got what you asked for. From the client's perspective, the client doesn't need to know the underlying work of the adapter or the adaptee. They just need to know how to make the request. The program takes in that request and does what it needs to give you the result of that request. So we have a nice encapsulation there. We have a nice separation of concerns. The client only needs to know what they know. They don't need to know how the system works. So good design, good OO design in that case. So the pattern itself, all we're doing, converting the interface of a class into another interface that the client expects. This allows you to communicate between classes that couldn't otherwise communicate because their interfaces aren't compatible. Their method names aren't the same, their method names, the way that one calls another isn't consistent or isn't what it expects. We can always write an adapter. And that will allow anything to be compatible. We can write an adapter for anything. The question is just how much work is the adapter? Sometimes the amount of work that is required for writing the adapter is going to be more work than just writing a brand new communication from scratch. So the design question that you're going to have to ask when you consider should I use the adapter pattern is weigh the amount of work that it takes to do the conversion versus the amount of work that it takes to implement it from scratch. If the conversion is less work, it's worth thinking about making an adapter for it. So general benefits, we have a decoupling between the client and the implemented interface. As the interface changes, we only need to modify the adapter and not any of the client code. Right? Nothing about the actual languages is changing. We just need to change how one converts from one to the other, if anything changes. So we change the adapter, not the source or the destination. We get to use the adapter with any subclass of the adaptee because we're adapting between interfaces and not concrete classes. So you do not want to write adapters between concrete classes because then if you ever abstract that into a hierarchy, your adapter only works with that particular concrete class. If you write an interface to interface adapter as we add subclasses to either the source or the destination, the adapter still works because you haven't made any assumption about the base class of either the source or the destination. That's a very important distinction. So here's what we look like. We have the client interacting with the target interface. And that's it. The client only sees the target interface. And then the adapter is going to figure out what the request is and pass it along to the adaptee as the specific request. So all the requests get delegated to the adaptee, which gets returned to the adapter, which gets returned to the client, and the client doesn't know that anything happened with this adapter or adaptee. They only interact with the target interface. Extremely useful. Adapter is found everywhere as requirements change. We're gonna take a little bit of an aside and talk about multiple inheritance because this is something that I've hinted at a couple times in the class, but it's worth talking about. There is one other kind of adapter that we don't really need to worry about in Java, but you will need to worry about in other classes if the position that you end up in, or you end up working in a position that uses a language that is not Java. So basic questions, how many classes can a Java class extend?
Only one.
One. Interfaces can we implement?
Many.
Arbitrary number. So as I've mentioned before, this is a Java specific restriction. Other languages support the concept of multiple inheritance, which is the ability to extend multiple classes. If you allow this, there is a big concern that you need to be aware of. There's nothing that prevents us from extending multiple classes except the class that the language doesn't allow it. Why does this restriction exist? And this is an actual technical term, it's called the diamond of death. Let's actually draw out the diamond of death. Here's the basic logic of what we're going to be doing. So we have classes A, B, C, and D in a nice diamond pattern. If we allow multiple inheritance, D is going to extend both B and C, and B extends A and C extends A. So we get this kind of inheritance relationship. This is not possible in Java because we do not have multiple inheritance. But when we do this, so B and C both inherit from A, D inherits from both B and C. B and C both override a method from A, and D does not override that method. So here we have a fly. Here we have an override for fly. Here we have an override for fly. D does not override fly. But because of inheritance, we can call fly on D. So if we say sum D dot fly, this is a legal thing that we need to do. So D now needs to decide, do I use this fly or this fly? Or even this fly? There's ambiguity that cannot be resolved. So this will crash your program if you do this. So whenever we have multiple inheritance in a language, this is something that you are allowed to program, and especially in a compiled language like C++, this is perfectly legal. This is a runtime error, not a compile time error. So this will compile. It's only when you try to run d.fly that your program crashes, and we can't specify exactly why. It's just you're going to get either completely unintended behavior or you get a crash. What's fun is that sometimes it doesn't crash, and sometimes it'll use this fly, sometimes it'll use this fly, sometimes it'll use this fly, depending on the language. The language reserves the right to tell you how this is going to work, and you don't necessarily get to specify. So just be very aware of this problem in languages that allow multiple inheritance. Not a problem in Java, because you can't do it.
So you call that again because it goes very well, or your program goes,
Who knows? You either get completely unintended behavior that's really difficult to debug. If one of the flies happen and you're expecting the other fly to happen, and you just get the wrong fly behavior, it's very difficult to debug that.
or it gets up and crashes, say screw you. Somehow I see like crash would be a preferable option.
If if the fly that you do isn't compatible with the D, then that's a problem. So we have 1 minute. When you have multiple inheritance, we can also, in addition to making what's the word I'm looking for? An interface adapter, we can make a class adapter. So an interface adapter adapts interface to interface. There's a source and a destination interface, a target interface. And if you support multiple inheritance, you can apply the adapter pattern to specific classes that have inheritance relationships. So we have something like the client, the adapter will extend both the target and the adaptee. So multiple inheritance just goes right in between them. And this is necessary in order to get the adapter to inherit the request and the specific request so that it can plug and play. But in order to get that behavior, you need to be able to extend both the target and the adaptee. I think that's what we have time for. We're going to get some real world examples of this and then talk about facade. But we're not gonna do so until Monday because we have to prepare for an exam and take an exam. So I will see you tomorrow for the study session. Please look at the study guide and come up with some questions so that we don't stare awkwardly at each other and we can fill up this period with good questions.
Double checking the final, it's not next Monday, but the Monday after.
Correct.
And when's the exam for you again?
Exam period this Friday, 2 days from now. Yeah, week and a half between them. And it will cover a lot of the stuff that we're covering right now. So that since we're covering it days before the first and the last next exam, there's no chance to put that on there. It's worth making sure you understand the material. So that'll be on the final. It's some generic questions about design patterns in general. But that's the only two in the sections.
Thank you.